We're going to spend some time analyzing parametric curves. We're going to come up with a lot of new terms, and so I just want to give you an overview of those terms that you can refer back to. So we're thinking about parametric curves. We're thinking about a function here that gives our position as a function of time. So it probably has, it's probably a function with either one input and two outputs, or that would be a plane curve, right? Of course, every plane curve, you could think about the xy plane as sort of being embedded within three-dimensional space. It's just a curve where the z-coordinate is just 0. And this is the general case, a space curve, then, where the value of our z-coordinate can change with time. So we're fully moving in 3 dimensions. Every plane curve is just a special case of that. So we'll just kind of analyze pretty much space curves, and then whatever we learn can somehow have application to plane curves because they are related. So if you imagine some parametric curve in space here, for example, maybe this is you're at an air show and you're watching an airplane go through aerobatic maneuvers, right? That it is performing. So you're sort of watching this curve now. From a fixed frame of reference on the ground, for example, the IJK frame of reference, then this motion is very complicated. But there's a more natural frame to view this from. If you think about it from the pilot's point of view, there's just a natural direction that would be straight ahead. If we make it a unit vector, that direction that is straight ahead. If the pilot was just to, at this instant, let go of the controls and let the plane just go in the direction he's going, then that's going to be the unit tangent. So we have a direction that's straight ahead. We have a direction in which the pilot is turning the plane. So we'll call that the normal, or the unit normal if we make it a unit vector. And then just to complete the frame, since we're in three-dimensional space, we'll need a unit vector that's perpendicular to these two. And of course, you could make a unit vector perpendicular to these two if you just cross them. So we'll make this binormal vector by crossing t and n. So the binormal will be t cross n. All right, the idea is that as we move along, as time changes, as we go along the curve, at every location we'll have a t, an n, and a b, and this is just a more natural frame of reference from the point of view of the motion. It's more natural to the actual curve to consider this frame, the TNB frame, as opposed to the IJK frame. We know how to find b. That's going to be t cross n. So what we need to do is to figure out how to find this unit tangent and this unit normal, this direction that's perpendicular to the curve, that's the direction that we're turning in. So first thing that we know is that the velocity, which is r prime of t, right, or v of t, is tangent to the curve. After all, in order to find the linearization, you use the velocity, which is the total derivative, right, to find the best line that approximates the curve. That's going to give you the tangent. Okay, so it's tangent to the curve. But what we want is a tangent vector whose length is always 1, just like I, j, and k, part of the IJK frame. Those have length 1. We want to make a unit tangent here that also has length 1. But that's easy to do as well, because we can make a unit tangent if we just take the velocity, which is tangent to the curve already, and divide it by its length. Anytime you take a vector and divide it by its length, it has length 1. So this is how we create the unit tangent. So if we have our parametrization, we're going to find the velocity, that would be r prime of t, and divide by the speed, which would be the length of r prime of t. That's simple. So we get our unit tangent. Now there's something else that we have already shown, and that's if a vector has constant length. For example, t now, since it's a unit tangent, no matter what time it is, it always has length 1. So t dot t is constant. Anytime a vector has constant length, you can take the derivative. We would get t prime dot t plus t dot t prime from the product rule. So that's equal to 0. Now the dot product is commutative, so t dot t prime is the same thing as t prime dot t. So really 2 times t dot t prime is equal to 0, and that means t dot t prime is equal to 0. So if we want a vector that's perpendicular to t, then we could just take the derivative of t, right? That's perpendicular to t. That's how we're going to create our unit normal. So our unit normal is going to be t prime. However, t is the tangent direction, right? If you're curving rapidly, then t prime could be large, or if you're slowly curving, then t prime would be small. The change in t would be small. So this is not necessarily a unit vector, but if we divide by its length, so we take t prime and divide by the length of t prime, then that is a unit vector. So this will be our unit normal. Okay, and then finally we're going to get our unit binormal by taking t cross n. So this will be our unit binormal.